In this video, we're going to talk about section 9.3. This is the last section in chapter 9. And this deals with expected value, normal distribution. We're not going to talk about simulations, but we will discuss odds. So all we'll look at in this section is expected value, normal distribution, and odds. Okay, so we'll start with expected value. Here we're going to calculate the expected value of a event. Okay. Now, we have calculated the mean of a collection of numbers using the expression x1 plus x2 plus and so on all the way up to xn divided by n. What we did was, when we found the mean, you have to add all the numbers together and divide by how many data values that you have in that set. Now here we're going to calculate the mean when we know the probability associated with each numerical outcome in a sample space. And in this situation, the mean is going to be called the expected value. Okay, so we're going to be calculating the expected value here. Let's suppose that you are playing a board game and your piece advances the number of spaces equal to the number where the arrow stops on the spinner shown, as in this case right here. Now, here we listed all the outcomes, a 1, a 4, and a 7, because those are the only numbers that are on that spinner. For a 1, the probability of getting a 1 would be 3/6, because there are 3 1s out of 6 numbers on that spinner. And for 4, the probability for that would be 1/6, because there's only 1 4 on that spinner out of 6. And for 7, it would be 2/6 for that probability, because there are 2 7s on that spinner out of 6 numbers. Okay. Now, if the spinner stops at 4, then your piece would advance 4 spaces. On average, how many spaces would your piece advance on each spin? So in this case, if we were to spin the spinner 6 times, then ideally we would expect a 1 to occur 3 times, a 4 to occur 1 time, and a 7 to occur 2 times. For these ideal outcomes, we get this. So using the definition of what a mean is, which is of course is the average, we just add those numbers that are on that spinner, 1 plus 1 plus 1, plus 4 plus 7 plus 7, and that's going to be divided by 6, because there's 6 numbers on the wheel, on that spinner. Now, on the next line, they're expressing this repeated addition as multiplication. The 1 is being added 3 times, so that's 3 times 1. The 4 is only going to be added 1 time, that's 1 times 4, and the 7 is being added twice, that's 2 times 7, and the whole thing is divided by 6. Okay. Now on the next slide, what they did here was they broke apart the fraction as 3 times 1 divided by 6 plus 1 times 4 divided by 6 plus 2 times 7 divided by 6. And then they express each fraction as a product. So this is like 1 times 3/6 plus 4 times 1/6 plus 7 times 2/6. And then express this as a probability. So here, that 3/6 represents the probability of getting a 1 on the spinner. So that's 1 times the probability of getting a 1. This 1/6 represents the probability of getting a 4. So that's 4 times the probability of getting a 4. And the 2/6 represents the probability of obtaining a 7. So this is 7 times the probability of obtaining a 7. So the sum of 1 times the probability of 1 plus 4 times the probability of 4 plus 7 times the probability of 7, obtained by multiplying outcomes and their probabilities. That's going to be 3.5 for this spinner. That means we should expect the piece to advance 3.5 spaces per spin on average. Okay, so this is how we calculate the expected expected value. And this is the definition here. So here we're going to replace the word mean with the phrase expected value. And that's when we compute a mean by multiplying outcomes and probability. So here's your definition. Suppose an experiment has k numerical outcomes, which is x1, x2, and so on up to x sub k with the corresponding probabilities. The probability of x1, the probability of x2, all the way up to the probability of x sub k. Then the expected value, which is going to be E of the experiment, is this formula. E is equal to x sub 1 times the probability of x sub 1 plus x sub 2 times the probability of x sub 2 plus and so on all the way up to x sub k times the probability of x sub k. All right, look at example 29. An organization holds a lottery as a fundraiser. It sells 1,000 tickets. There are 10 winning tickets where one winning ticket pays $750, 3 winning tickets pays $200 each, and 6 winning tickets pay $50 each. What is the expected value of a lottery ticket? So here we're going to look at getting that expected value using that particular formula that I gave you. So here the table does show the outcomes and probabilities for the lottery. Okay. The outcome for $0, that probability is 990 out of 1,000. The reason for that is this. There are 1,000 tickets and only 10 of them have winning amounts. The other 990 will not. So the outcome for 0, that probability would be 990 out of 1,000. For $50, there's 6 winning tickets for $50 each. So the probability of winning $50 would be 6 over 1,000. And for $200, there are 3 winning tickets out of 1,000 for that amount. So that probability would be 3 over 1,000. And only 1 winning ticket for $750, that probability of winning $750 would be 1 over 1,000. Okay, so the expected value or the average payout per lottery ticket is going to be this. E is equal to 0 times 990 over 1,000 plus 50 times 6 over 1,000 plus 200 times 3 over 1,000 plus 750 times 1 over 1,000. Compute that, you'll get $1.65. That would be the expected value or the average payout per lottery ticket. Okay. All right, take a look at problem number 2. This is on page 252 in your book, where it says here, determine the expected value of the spinner. Okay. And as you can see, I've already worked this out, but I would cover this up and just have you follow along for each line. Notice here that the 5, this space is about 25% or 1/4. The rest is for the 12. That represents 3/4 of the circle. Okay, so that means the probability of obtaining a 5 would be 1/4. And the probability of obtaining a 12 will be 3/4. Okay. And now we can find the expected value. So to find the expected value, it would be this. E is equal to the 5 times the probability of getting a 5, which is 1/4, plus the 12 times the probability of getting a 12, which would be 3/4. Now, I've already did this on the calculator, so if you were to do 5 divided by 4, and then 12 times 3 divided by 4, and then add the 2 together. In fact, I'll do it here. This will be 5 divided by 4. And then that'll give you 1.25. And then 12 times 3 divided by 4. Excuse me, that'll be 9. So if I take that 9, add that to the 1.25, you'll end up getting 10.25. That would be the expected value of this particular spinner. Okay. All right. Now let's look at another problem in the book, problem number 17 on page 544. The table shows the outcomes and probabilities for a four-sided die. What is the expected value of the die? Okay, so here's that table with each outcome, 3, 4, 6, and 7, and each of the respective probabilities here. So all we have to do there is take each outcome, multiply by its respective probability. So I do 3 times 0.20 plus 4 times 0.15, and then plus 6 times 0.35, and then plus 7 times 0.30. So pretty much you can just do all of this in the calculator, and you'll end up with 5.4. And if you want me to, I can show you how that's done in the calculator. I'm using a TI 84 plus calculator. So here you got 3 times 0.20 plus, I need to bring this down a bit, 4 times 0.15 plus 6 times 0.35 plus 7 times 0.30. And you get the expected value of 5.4. Okay. All right. Take a look at problem number 13 on page 543. This is another one of those expected value problems here. A game consisting of tossing 3 coins. If all 3 coins lands on heads, then the player wins $75. If all 3 coins lands on tails, then the player wins $45. Otherwise, the player wins nothing. On average, how much should a player expect to win on each game? Okay. First of all, I had to get the probability for getting the heads, getting 3 heads, and the probability of getting 3 tails. Okay. Now, if you toss a single coin, you're either going to get heads or tails. So the probability of getting a head on one toss is 1/2. And the probability of getting a tail on one toss would be also 1/2. Okay, so here's what we got. On the first toss, the probability of getting a head would be 1/2. On the second toss, that same probability of getting a head is also 1/2. And the same thing here for the probability of getting a head on the third coin, 1/2. So this is where we have to multiply 1/2 times 1/2 times 1/2. That's going to equal 1/8. So the probability of getting 3 heads would be 1/8. And for tails, it's the same thing. Probability of getting a tail would be 1/2. And the same is on the second coin, the same on the third coin. So that probability of getting 3 tails would be 1/2 times 1/2 times 1/2, which is also 1/8. Okay, so now we can find out what the expected value is going to be. Okay, that would be 1/8, which is the probability of getting the heads, times the amount that the player will win if all 3 coins lands on heads. That's $75. Plus 1/8, which is the probability of getting a tail, times the amount that the player will win if all 3 coins lands on tails. That's $45. Now the 6/8 come from the fact is if they don't get 3 heads or they don't get 3 tails, they're going to get something else. There are 8 possibilities, by the way, so that's where the 6/8 comes from. And that has been multiplied by 0 because it says otherwise the player wins nothing. Now, if you do 1/8 times 75 will be 9.375, and then 1/8 times 45, that'll be 5.625, and then 6/8 times 0 is 0. Add these together, you'll end up with 15. So in this case here, the players should expect to win $15 on each game. That's your expected value. Okay. So that's how we use expected value in these particular cases. All right, next we're going to talk about standard deviation. I'm not sure why they put standard deviation in this section, and I say that because standard deviation is considered to be a measure of variation, which we talked about when we were dealing with the range and the variance. All right, now here we're going to let X bar denote the mean. If you recall, when we were doing the chapter on statistics, we were dealing with the mean. So X bar is the mean of the numbers X1, X2, X3, and X4. We're just saying that. The measure spread of the numbers X1, X2, X3, and X4 is the standard deviation, and that will be denoted by a lowercase s, which uses the square rather than the absolute value of the deviations. So this is the formula for finding the standard deviation here. S is equal to the square root of the quantity x1 minus x bar squared plus x2 minus x bar quantity squared plus x3 minus x bar quantity squared plus x4 minus x bar quantity squared. That's all divided by 4. Okay, now this is not just limited to 4 data sets. Here, we can use this for more than 4 data sets. So, in this case here, if there were 5 data sets, then you'll have like 5 differences, 5 squares of the deviation, that'll be divided by 5. But for this particular section, we're only dealing with 4 data values. Take a look at this example. Wally grew 4 sunflower plants. The heights were 171.6, 174.6, 174.4, and 175.4 centimeters. And here we're going to calculate the standard deviation of the heights of the sunflowers. So in this case here, we first find the mean of those data values there. So here we add 171.6, 174.6, 174.4, and 175.4. So here we're going to add those together and divide by 4. You'll end up with 174 centimeters. Now, on the next slide, here they calculate the standard deviation using this formula here. Now, notice they give us a table of how to do the standard deviation. What they did here is list all the data. Those 4 data values there are listed. And then second, they computed the deviation from the mean by taking the data value and they subtract from it the mean of 174. So in this case, they did 171.6 minus 174, you'll get negative 2.4. And then 174.6 minus 174 will be 0.6. And then for the next one, 174.4 minus 174 would be 0.4. And then the final one, 175.4 minus 174, that's 1.4. And then the next column, they squared the deviations here. So here, if you take negative 2.4 and you square it, you'll get 5.76. Here, if you square a negative, you're going to get a positive value. And then 0.6 times Well, 0.6 squared would be 0.36. And then 0.4 squared would be 0.116. 0.16. And then 1.4 and u squared would be 1.96. And then here they took the sum of the squares of the deviations here. They added those numbers together that we got in column 3 to get 8.24. And then they computed the standard deviation, which is this. The square root of the sum of the squares of the deviations, that's 8.24, divided by the number of data values that you have. In this case, it's going to be 4. So 8.24 divided by 4 will be 2.06. Take the square root of 2.6. This will be approximately 1.44. So that means the standard deviation is going to be 1.44 centimeters. And that is a representation of the spread of the heights. Okay. All right, take a look at this one, problem number 48, parts A and B on page 546. Now, that problem, number 48, does have a part C and a part D to it. I'm going to do those later on. But for now, I'm just doing parts A and B. And we're going to be using that to answer part C and D later on in this section. It says here the data set consists of the scores 42, 58, 60, and 52. And there are two parts in this case that we're dealing with. Part A, calculate the mean. Well, this is what we do. We take this X bar, that's your mean. We add these data values together. And there are 4 data values, so we divide by 4. So add 42, 58, 60, and 52, you're going to get 212. 212 divided by 4 would be 53. Okay, so the mean for that data set would be 53. And now part B is to calculate the standard deviation. Now notice I created a table here. The first column is the X, that's your data values here. The second column would be that each X value would be subtracted from your mean. And then this column is just going to be the square of what I got in this second column. That's X minus X bar quantity squared. So for this deviation, if I do 42 minus 53, which is your mean, that's negative 11. And then for the 58, if I do 58 minus 53, that would be 5. For the 60, 60 minus 53 will be 7. And then for the 52, 52 minus 53 would end up being negative 1. And then I'm going to square each of these deviations here. Okay, so if I square negative 11, that's negative 11 times negative 11, which will be positive 121. If I square the 5, 5 squared, 5 times 5, that's 25. Square the 7. 7 times 7 will be 49. And then negative 1 squared, negative 1 times negative 1 will be positive 1. And then next, I add those numbers here. Add the squares of the deviations. Add 121, 25, 49, and 1, you'll get 196. And now, to find the standard deviation, that's going to be the square root of the sum of the squares of your deviations. That's 196 divided by, and there are 4 data values, we divide by 4. 196 divided by 4 would be 49. And then you take the square root of 49, you'll end up with 7. So the standard deviation for that data set would be 7. Okay. Next, we'll talk about the measure of position using a z-score. Okay. So here we're going to be using a z-score to find the measure of a position. Right. So here, the following is the definition of a z-score. So here's that definition. Here we're going to let x be a number from a collection of numbers. The z-score for x is the number z equaling to the x value that you're dealing with minus the mean. That difference will be divided by the standard deviation. And that will give you your z value. Now, the z value will be negative. If it's negative, that means your x is going to be to the left of the mean. And if z is positive, your x will be to the right of the mean. Now, the z represents the number of standard deviations your x value is from that mean. And we can think of x as a raw score and the z as a standardized score. Okay. And I do need to mention here, when you're calculating the z-score, you always round the z value to 2 decimal places. Make sure you round the z value to 2 decimal places. So in this example, the average monthly rainfall in London is 6.3 centimeters per month with a standard deviation of 1.14 centimeters per month, and the average monthly rainfall in Seattle is 8.08 centimeters per month with a standard deviation of 4.57 centimeters per month. Suppose during a particular month it rained 7.67 centimeters in London and 12.88 centimeters in Seattle. Which city received relatively more rain than usual? Okay. So in this case, here we're comparing the rainfall amounts of 7.67 and 12.88 centimeters for two cities that have different means and standard deviations. So we compare their z-scores to make a relative comparison. So the z-score for the rainfall of 7.67 centimeters in London is going to be calculated as this. Z is equal to 7.67 minus 6.3 in parentheses divided by 1.14. The 7.67 is that data value that we're dealing with. The 6.3 is your mean for London, and 1.14 is the standard deviation. And of course, we round to 2 decimal places. So if you want to, you can put this in the calculator as you see it up here. So if I do left parentheses 7.67, well, let me just do this. 7.67 minus 6.3. That'll give you the 1.37, and then divide that by your standard deviation of 1.14. Now you have to round that off to 2 decimal places, so that would be approximately 1.20 as a z value. What that means here is that for that particular month, that rainfall in London is 1.20 standard deviations above the mean. And then the z-score for the rainfall of 12.88 centimeters in Seattle would be 12.88 minus 8.08 with the difference divided by 4.57. So here, 12.88 minus 8.08, that will leave you with 4.8, and I'm going to divide that by 4.57. You'll end up with approximately 1.05. What that means here is this. The rainfall in Seattle for that particular month is 1.05 standard deviations to the right of that mean. Okay. So here the rainfall in London, as I mentioned, is 1.20 standard deviations above the mean, while the rainfall for Seattle is 1.05 standard deviations from the mean. Therefore, London received relatively more rain than Seattle compared to the city's usual amount. Okay, because that Z value for the rainfall in London was higher than the Z value for the rainfall in Seattle. Okay. All right, take a look at problem number 11 on page 543. Joey took a quiz in his math class. The mean was 72 points and the standard deviation was 10 points. Mitchell scored 86 points on a quiz in his history class, which had a mean of 74 points and a standard deviation of 5 points. What is the minimum score that Joey should have earned to score relatively higher than Mitchell? And show your work. So here's the work that I showed you, but I'm going to go through this step by step. So we're looking for Joey's minimum score. So we left that blank. Now, he took a quiz in his math class. Here, the mean is 72 and the standard deviation is 10. Here, S is the standard deviation. Mitchell scored 86 on a quiz in his history class. For the history class, that mean was 74 points and the standard deviation was 5 points. Okay. So the first thing I did here was found out the Z-score for Mitchell because I know what he scored on his history test. And I know the mean and the standard deviation for that history class altogether. So I'm going to use Z is equal to X minus the mean divided by the standard deviation. So for Mitchell, his score was 86. So this will be 86 minus the mean is 74. And that's divided by 5. So 86 minus 74 will be 12. 12 divided by 5 will be 2.4. So the the Z-score for Mitchell is 2.4. Now we're going to use that 2.4 to help us find the minimum score that Joey should have earned to score relatively higher than Mitchell. So we're going to find the minimum score using the same Z formula. Z is equal to X minus the mean, all divided by the standard deviation. The Z is that 2.4. And then that's going to be equal to Joey's test score or quiz score in his math class. We're going to make that be X minus the mean for that math class was 72. And the standard deviation for that math class was 10. Now what I did was put the 2.4 over 1 because I'm going to do cross multiplication here. So if I do 1 times X minus 72, this will be X minus 72. And then 2.4 times 10 will be 24. So I have an equation I'm going to solve for X. So to get X by itself, I had to add 72 on both sides to get X is equal to 96. So 96 will have to be the minimum score that Joey should have earned to score relatively higher than Mitchell. Okay. All right. Take a look at problem number 12 on page 543. It says here, Ben scored 82 on a history test, which had a mean of 74. Molly scored 88 on a math test, which had a mean of 80. The Z-score for Ben was 1.4, and the Z-score for Molly was 0.8. Which class had test scores with more variation? And you want to show your work. So here, Ben had a test score of 82. Its mean was 74. And then Molly had a test score of 88 on the math test. That mean for that was 80. Now the Z-score for Ben was 1.4 and the Z-score for Molly was 0.8. So for each one of these, we're going to find the standard deviation. Okay, so now let's start with Ben's. uh, history test and the history class itself. Okay. So as you can see here, I have to use z is equal to x minus the mean divided by s, which is your standard deviation. The z in this case is 1.4, and that's equal to x, which is Ben's score of 82, minus the mean, which is 74. That's going to be divided by s. So if I do 82 minus 74, that's going to be 8. So I got 1.4 is equal to 8 divided by s. Now, in this case here, I had to multiply both sides by s, because I got the s in the denominator. So here this will be 1.4s, and that's equal to 8, because these s's divide out. And then, to solve the s, you divide both sides by 1.4 to get s's equal to, well, it's going to be approximately 5.7. So the standard deviation for the history class would be 5.7. And then we're going to look at Molly's situation in the math class. We're going to use that same z-score, z formula. Z is equal to x minus the mean divided by s. So here, your z is 0.8. The x is Molly's math test score of 88 minus the mean of 80 divided by s. So your standard deviation is what we're going to find here. So 88 minus 80 will be 8. So I got 0.8 is equal to 8 divided by s. And of course, to solve, well, to get that s out of the denominator, I have to multiply both sides by s. So it'll be 0.8s is equal to 8. And then divide both sides by 0.8, you'll get s is equal to 10. So the standard deviation in that math class was 10. So which class had test scores with more variation? It was the math class, because their standard deviation was 10. So the scores on the math test had more variation. Okay. So that's how we calculate z-scores, and we can also use that to find an x value or find the standard deviation as well. Okay, next we're going to look at normal probability distributions. Okay, so we're going to be talking about the normal curve here in this case. We have mentioned 3 important aspects of a quantitative variable, which is a numerical variable. Measures of center, measures of variation, and distribution. The distribution tells us the shape and pattern of the possible values. We can use a graph to display the shape and pattern of the values. The distribution also gives you a sense of the possible values of the variable and how to use and how often these values occur. So, for discrete values such as the outcomes when we roll a die or spin a spinner, we could use a table to display the distribution. For example, let's consider a spinner with 8 equal-sized sectors that have the numbers 1, 4, 4, 5, 6, 7, 7, and 14. Then the mean is 6 and the standard deviation is 3.5, which is rounded. We can display the distribution of the discrete values using the probabilities, as you can see here. Here you got your x values on the top row, and on the bottom row is the probability for each individual x value. Like the probability of 1 would be 0.125, because there's only one number that has a 1 out of 8. So 1 divided by 8 would be 0.125. For the 4, that probability, again, the 4 would be 0.25 because there are 2 4s out of 8, and so on. And then for many variables such as height or blood pressure, we can use a histogram to display a big picture of the shape and the relative frequency with which values occur in intervals. So in many situations, the histogram is symmetric with the shape of a bell, such as the one in figure 10, as you can see here. And this is what the normal distribution looks like. We also call that the bell-shaped curve or the normal curve. Okay. So if quantitative data have a symmetric bell-shaped histogram, then the variable is said to have a normal distribution, also called a bell-shaped curve. And the peak of the bell is above the mean. If the histogram displays the relative frequencies or percents, then the total area of the rectangles will be 1. Okay. So in example 33, suppose the scores on the SAT are, quote, normally distributed, end quote. What does this mean? Well, it means that if you take a random sample of many SAT scores and then create a histogram for the data, then you should expect to see a histogram that is symmetric with the shape of a bell. So normally distributed means it's going to become a normal bell-shaped curve. Okay. All right, next we'll talk about the 68, 90, 95, 99.7 rule for normal distributions. Okay. An amazing aspect of a variable, such as for heights or test scores that is normally distributed, is that we can say something about the percent and therefore probability of observations that should belong to intervals. All we need to know is that the shape of the histogram meets our description. Symmetric in the shape of a bell, along with the mean and the standard deviation of that data. So here is that 68, 95, 99.7 rule. We're going to assume or suppose that data have a histogram that is symmetric and shaped like a bell. So the first bullet is this: approximately 68% of all data values fall within one standard deviation of the mean. That is on the interval x bar minus x to x bar plus x. One standard deviation below and one standard deviation above. Then the next bullet is approximately 95% of the data values fall within two standard deviations of the mean. That's from x bar minus 2s to x bar plus 2s. So that means two standard deviations below the mean and two standard deviations above the mean. And then approximately 99.7% of the data values fall within three standard deviations of the mean. That means x bar minus 3s to x bar plus 3s. That's three standard deviations below and three standard deviations above the mean. Okay, so this represents the concept map to visualize the 68, 95, 99.7 rule. So here, this green line here represents one standard deviation of the mean. That's within one standard deviation of the mean. Approximately 68% of the values fall within this interval. And then the blue line represents two standard deviations in that interval. Approximately 99% of the values will be in that interval within two standard deviations of the mean. And then finally, this red line, this long red line, represents 99.7% of the values that are within three standard deviations of the mean. Okay. All right, next we'll look at example 35. The mean SAT score for high school students on the mathematics portion of the test in 2010 was 516, with a standard deviation of 116. Here we're going to assume the scores are normally distributed. Estimate the percent of students with the following scores. Part A is between 400 and 632. Part B between 400 and 748. Part C less than 400. And Part D more than 284. So here, we're going to draw a number line with the mean of 516 in the center. And then we number the equally spaced tick marks that are 1, 2, and 3 standard deviations from the mean. So in this case here, for example, that 516, that's going to be in the middle. Like what we have here. 516, that's going to be in the middle. That's your mean. So, one tick mark to the left of the mean, we have to subtract 116 from the 516 to get 400. Now, you can continue to subtract 116 to get this number and this number here. So, 400 minus 116 would give us this 284, and 284 minus 116 would give us that 168. And then on the right side, we add 116. Because these represent values above the mean. So 516 plus 116 will give you 632. That's one standard deviation above the mean. 632 plus another 116 will be 748. And then 748 plus another 116 will give you the 864. Okay. And then we can use symmetry and the 68, 95, 99.7 rule to calculate the percents for each interval. Like on this next slide that you see here. Now notice, your mean is 516. Within one standard deviation of the mean, that's 68%. But they're equally marked off. So if you divide 68 by 2, you'll get 34%. 34% here, and 34% here. And then next, within two standard deviations of the mean, that's 95%. Two standard deviations of the mean. 95%. Well, we already got 68%, so if you subtract 68 from 95, you should get 27. And then 27 divided by 2 will be 13.5. So 13.5 would be here, and 13.5 would be here. And then finally, for three standard deviations, would be 99.7%. Well, we already got 95, so 95 from the 99.7 would be 4.7. 4.7 divided by 2 will give you 2.35. That 2.35 will be here, and 2.35 will be here. And then if the whole normal curve has an area of 1, then 1 minus 99.7 would leave you with 0.3. And 0.3 divided by 2 would be 1.15. So 1.5 is on the far left and 0.15% is on the far right. So that's where they're getting those numbers from, those percentages from. Now, let's answer those questions in parts A, B, C, and D. Part A asks for the percentage of students with the following scores between 400 and 632. Well, here's 400, and that's 632. Each of these is 34, so 34 plus 34 gives you the 68. And then part B, between 400 and 748. That's these two numbers right here. So now you got 34, 34, and 13.5%. Add those up, you get 81.5%. And then for less than 400, here's 400. We have to look at everything to the left of 400. 13.5%, 2.35%, 0.15%. Add those together, you'll get 16%. And then finally, more than 284. Here's 284 right here. That's everything to the right. So I got to add 13.5%, 34%, 34%, 13.5%, 2.35%, and 0.15% to get 97.5%. So that's how we answer those particular questions. And we can use this particular number line that we have here to answer problem number 51 on page 546. Okay. The mean SAT score for high school students on the writing portion of the test in 2010 was 492 with a standard deviation of 111. What percentage of students have the following scores? So in part A, we'll start with more than 714. Well, we need to create a table first, which is what I did here. The middle is the mean. That's the 492. To get these numbers that are above the mean, we'll keep adding 111 each time. So like that 492, I had to add 111 to get 603. And then add another 111 to get 714. And the 111 to the 714 would give me 825. And then to get the numbers on the left side of the mean, we have to subtract 111 each time. So 492 minus 111 is 381. 381 minus 111 would be 270. And 270 minus 111 would be 159. And these percentages up here are the same as the ones that we have here in this one. So I'm just copying those over. And then we can answer our questions here. So in this case here, more than 714. Here's 714. I got to look at everything to the right. So 2.35% and 0.15%. Add those two together, you'll get 2.5%. So the percentage of students who have test scores, SAT scores, more than 714. And then next is less than 381. Here's 381. I need to look at everything to the left of 381. So in this case here, 13.5, 2.35, 0.15. Add those up, you'll get 16%. So that represents the percentage of students who have SAT scores less than 381. And then between 381 and 714, that's these two numbers here. I need to look at 34%, 34%, and 13.5%. Add those numbers together, you'll get 81.5%. And then between 270 and 492, that's this right here. If I look at 13.5% and 34%, add those two together, you'll get 47.5%. That would be the percentage of students who have SAT scores between 270 and 492. Okay. All right. Now, there is a part 2 to this video on section 9.3, so be on the lookout for that particular video as well. That will cover things like usual values and odds in favor and odds against. Okay, so look out for that video as well.